Welcome to the Daily Space for Thursday, July the 5th of 2018. I am your host, Dr. Andres Plazas, and today we're going to talk about news from space and astronomy and some historical news as well. So I guess they're not news anymore because they're historical. But anyhow, what I wanted to say is that today we have two stories. So the first one is about the galaxy formation, galaxy evolution. And then for the second story of today, I want to talk about Newton's mathematical principles of natural philosophy that was published on a day like this in 1687. So I thought it was cool to talk about that. But let's start first with our first story of the day about the galaxy formation. And let me change a little bit here. Now you see a pretty galaxy next to my face. There you go. So this is a story from researchers from the Institute of Astrophysics and Space Sciences in Portugal. And it's a story about that gives us insight into the nature and formation of the central spherical component of spherical galaxies, of what is known as the bulge. So a spiral galaxy is a galaxy such as the Milky Way, as you guys know, or the Andromeda M31, the galaxy in M31. And the story that we bring today is interesting because according to the researchers of this study, the bulge, or the central spherical part of these spiral galaxies, is thought to form in two distinct ways. So the first way is that what they call the classical bulge, and in this scenario, the classical bulge consists of ancient stars that they are older than the disk, and this is so because they assembled quickly about more than 10 billion years ago, before the disk assembled, the disk itself. So first came the bulge and then came the disk. And then the other alternative in the standard theory of galaxy formation tells us that actually the bulges form from the disk. And so this is referred to as a pseudo bulge. And in this scenario, the stars of the bulge have similar ages as those stars of the disk, because they assembled gradually through a combination of dynamical processes that led to a continuous star formation from the disk into the bulge. So, of course, these are two very different scenarios, and people were puzzled by this, because they are going to produce different predictions. These two scenarios imply that the classical bulges and the pseudo bulges, as I said, have very different characteristics. And up until this study, this sharp contrast was never observed before. So the researchers from this institute in Portugal, they used integral field spectroscopy. So we have talked about this method in the past, but just as a reminder, in integral field spectroscopy, the signal from each pixel on the detector is sent into a spectrograph that splits the light of the galaxy. And then you can have a spectrum per pixel, and then you can have a simultaneous recording of thousands of spectra per galaxy, and in this way you can produce a spatially resolved three-dimensional view of the stars and the ionized gas of a galaxy using this technique. They also use a different way, a new way of modeling the galaxy, and so they took observations of more than 500,000 individual spectra to spatially resolve the star formation history of the bulge and the disk components of about 135 galaxies from a survey called the Khalifa 3 survey. So what did they find? Well, what they found actually implies that the formation timescale of bulges is inversely related to the total galaxy mass. So what does that mean? That the bulge formation in massive galaxies is completed within the first 4 billion years of cosmic evolution or so. However, this formation is still going at a low pace in galaxies that are less massive. So it's basically inversely proportional to the mass uh, of the galaxy. And this is actually an explanation that provides an unification between these two ways of generating the bulge of a galaxy. Because the authors claim that this study reveals a continuity in the properties of the bulges, as I said, and it actually said that instead of having these two strikingly different opposite formation scenarios for the bulge of the galaxy, the classical bulge and the pseudo bulge, they said that the bulge growth is driven by a superposition of a very quick and early, and a slow and secular processes, and the relative importance of these two processes, like quick and slow, is regulated by the mass, by properties of the galaxy such as the mass and the density. Um, so this is in the press release, the researchers claim that this is has been one of the main questions in the field of galaxy formation. But at the same time, with this data, the researchers had another goal in mind, and it was to assess the role of active galactic nuclei in the formation of galaxies. And they found actually that these active galactic nuclei, or AGNs, are actually the dominant source of gas ionization in bulges that are very massive, but they are negligible in bulges that are younger and they have lower mass. This is also something that provides insight in the understanding on the coevolution between the bulges and the supermassive black holes that you find at the center of galaxies such as the Milky Way. So yeah, so this is the first story of the day that I wanted to share with you guys. And it was a little bit of a slow day as well in the news. So I don't know, maybe people are coming back from the holiday. But yesterday, Pamela was talking about an important historical note about Henrietta Leavitt and the variable stars that she measured, and how her work allowed us to measure the size of our neighborhood. And then today, when I was reading at the news, I also, well, looking for the news, I was remembered that in a day like today, in 1687, it was published what some people call the most important book in science, and I thought I would talk a little bit about it with you. So this is as you guys know, as I said, this book is called The Mathematical Principles of Natural Philosophy. That's how you used to refer to physics back in the time, as natural philosophy. And it's a work in 3 volumes, or in 3 books, by Isaac Newton. It was published in Latin. That was the language of science of the time. And the first edition, as I said, was published on July the 5th of 1687, and then Newton published other editions in 1713 and 1726. The mathematical principles, or the Principia in Latin, this is how we refer to this book. They state what we call the Newton's laws of motion, the 3 laws of motion of Newton. And these are the laws that form the foundation of classical mechanics, what we know as classical mechanics. But it also, for the first time, gives us a mathematical prescription of what is called the law of universal gravitation, the universal law of gravitation. And it also has a derivation of the laws of Kepler of planetary motion. Johannes Kepler had already produced some laws that explain the motion of celestial objects in the solar system, but he obtained this from an empirical point of view, using observations by his mentor, by Tycho Brahe. So the Newton's laws of motion, they describe the relationship between a body and the forces that act upon it, and also the motion of a body in response to those forces. So this book, as I said, is considered as one of the most important works in the history of science, and no other work was more seminal in the development of modern physics and astronomy than this book. For example, one of the main conclusions of the book is that the force that is responsible for the cinematics of the for the motions of the planets in their orbits, it's actually the same in kind as the one that is responsible for terrestrial gravity. So in other words, Newton unified the laws of the heavens and the laws of the earth in a way with the law of universal motion. And this concept of unification um, started to be fundamental in physics, because now from that point on we started to look at the fundamental laws of science, of physics, that apply not only in particular circumstances but apply to many other circumstances. And then from that point on, the quest from unification has been what some people refer to as the holy grail of physics. One example of unification then came in 1865, when James Clerk Maxwell unified the laws of electromagnetism, the electrostatic laws and magnetism and magnetic laws in electromagnetism. So that was another example of unification. And nowadays we are trying to figure out how can we unify the current theory of gravity that we have is Einstein's theory of gravity, that was an extension of Newton's theory, and quantum mechanics, the pillars or foundations of modern physics. We're trying to find a theory that unifies them, and we could say that we could trace this idea of unification back to this time in Newton. And well, yes, as I said, then Albert Einstein came about 300 years later from Newton's publication of this book, and then Einstein showed that Newton's laws applied in a certain constants, in a certain limit, when you are not approaching the speed of light, for example, or where the scales in which you're talking about are not microscopic. Then this was the revolution that happened at the beginning of the 20th century and the end of the 19th century. At the end of the 19th century, between the publication of Newton's Principia and the end of the 19th century, people started to. So of course came the Enlightenment, came the Industrial Revolution, and then all of this part of the scientific revolutions fundamented by Newton. But then by the end of the 19th century, people thought that they were actually done with physics. Like, okay, Newton works, this is great. But then there were some certain observations that didn't fit the bill, right? So Newton's theory was so successful for all these years that people were almost thinking that, okay, we're done. Then at the beginning of the 20th century, we started to have the revolution from quantum mechanics and the revolution from the theory of Einstein, general relativity. But in the end, even these two theories, and this is something that you learn when you read the physics textbooks, in certain cases, the quantum in the limit cases, the theory of quantum mechanics and general relativity, they reduce to the theory of Newton. So when you look at this in excuse me, in retrospective, despite the fact that we know that there is something beyond Newtonian mechanics, we have to acknowledge that the publication of this book was a turning point in the history of science, and many people today still consider Newton as the greatest physicist of all, and then followed by Albert Einstein, followed then Einstein as number two. And Newton himself, just to comment a little bit more about this, Newton himself also, he didn't just come out with this just out of the blue, right? He also acknowledged that he had, in his own words, stood on the shoulder of giants. He said that if I was able to see beyond, it's because I stood on the shoulder of giants, and by that he was acknowledging the contribution of scientists that came before him, such as, of course, Galileo, Copernicus, Johannes Kepler, Tycho Brahe, Christian Huygens, Robert Hooke, Descartes, well, you know, and many of them, they also had already come up with some of the ideas that Newton presented in his book. They had come up with the idea that some of the laws of motion, some of ways of explaining the movement of celestial bodies. But the main contribution of Newton is to, of course, to put it in the foundation, in a mathematical foundation. Although Galileo did a little bit of that, but Newton put it in a mathematical foundation, and he invented a new branch of mathematics that we know today as calculus, the differential calculus. Then Leibniz and Newton came to be known as the founders of calculus. And he also started to explain why things are. So he was able to derive the laws of Kepler. Kepler had his laws of planetary movement, but Newton was able to show that if you assume something more fundamental, if you assume the fundamental law of gravity that he proposed, then you can derive from a logical point of view these laws that Johannes Kepler had derived from an empirical point of view. And yeah, so this is one of the most amazing, of course, works in the history of science as well. And I just wanted to mention today a little bit, to talk a little bit about this. So back in the time when Newton published the Principia, well, of course, it received some criticism, and many of the people, many of the scholars couldn't even decipher it. Even people like Leibniz and Huygens, they found that it was very hard to actually follow the geometrical derivations that Newton laid down. But in the end, in the next century, then people like Clairaut, or people like Lagrange and Laplace in France, they started to develop this classical mechanics and show the greatness of the world, the foundations laid down by Newton. Then in the next century, of course, we came out with a new formulations of classical mechanics. And then people started developing a new foundation for thermodynamics, but all of this was inspired by classical mechanics, and people started to understand, for example, heat in terms of not like a fluid that goes from hot objects to cold objects, but by the individual movement of the kinetic energy of atoms in a Newtonian way, in a subatomic way. So all of this was influenced by Newtonian mechanics, of course. And nowadays, again, as I said, we already know that there's something beyond Newtonian mechanics, that is not a complete theory, but it's perfect for everyday purposes. Even all the there are certain cases when you have to make adjustments due to relativity or different strengths of gravitational field, but for most of the celestial mechanics that we use nowadays to send rovers to Mars and stuff, these are simply the laws of Newton. You don't need to resort to general relativity for those things. And some of you who know me and who have seen me give news here in the daily space, and you know that I've talked about cosmology in the past, and there are situations in cosmology where we do have to resort to Einstein's gravity, the theory of gravity. That's the most fundamental theory of gravity. But Newton's theory remains like the like a standard case for the everyday gravity situations that we encounter. So yes, I just wanted to pay a little homage to the mathematical principles of natural philosophy and the importance and the turning point in the history of science. So yes, maybe you guys can give me some comments or questions. Let me see. Now I'm gonna check what you guys read, what you guys wrote. Um, Hello. So we have a comment by Sirora. So regarding the first story of the day, I have also heard that the lack of these bulges also means that there will be no supermassive black holes. Yeah, I'm not an expert at that, but I believe that's the case. That's one of the implications that they did with the study. They were also looking at the relationship between these bulges and the active AGNs, active galactic nuclei, and the existence of a supermassive black hole in there. So, is this the book that covered calculus? So, this is a comment by Hannes Svorwerp. As I understand it, so Newton started developing what is called the differential calculus, but in a very geometrical way. And he started to toy around with the concept of something that is infinitesimally small. So something that is very, very, very tiny. And then if you can take the ratio of two quantities and then you can imagine that then that quantity starts to be those quantities start to be very, very small. Then you start coming with the notion of limit. And then when you come up with this notion of limits in mathematics, then you are coming up with the notion of calculus. So, but what is calculus? So, just to back it up a little bit, mathematics in general is the study of structures, and in particular, calculus is the study of the structures of change. So, um, as we know, as we can agree, there's like Heraclitus, for example, used to say in ancient Greece, like you don't shower, you don't bath yourself twice in the same river. That does that mean he was trying to say that everything in the world is changing. So in physics, in the end, we realize that we want to describe the state of a physical system as a function of time and how it changes in time. So from that point of view, it's in a way natural to see how Newton had to develop a structure in mathematics that dealt with things that change, in particular the things that change with time. So calculus is just the study of changes, of the structures of change. Then years later came Gottfried Leibniz, a rationalist, a philosopher and mathematician from Germany, who also developed calculus. And then back in the time there was a very big dispute between Newton and Leibniz, and Newton was then the head of the Royal Society, and he even used his power to discredit Leibniz. But then in the end we conclude that calculus was developed at the same time by these two characters, differential calculus and integral calculus. Leibniz came up with the symbol of the integral. So yes, I think somebody else was also replying to that question as I'm reading. I'm catching up. The way I usually do it is I just talk and then I look at the chat. So forgive me for that. So Larry says, I tried to read an English translation of the Principia once. There are no equations. Everything is written out in Elizabethan obtuse prose. Yes, I think I myself tried to do that once when I was in college. I went to the library, and it's like, oh, neat, a copy of Newton's Principia. And it's like, oh, wow, a lot of geometrical derivations, and I guess in the spirit of Euclid, I guess the elements of Euclid, and it's definitely not easy to follow. So Newton said that, Larry said. So I think that you're referring about the standing of the shoulders of giants. And last time I checked, he wrote that in a letter to someone. But it good to be good to do some fact checking. But I did do some research on this, and I believe that Newton did actually wrote that to a letter to someone that if he was able to see beyond is because he was standing on the shoulders of giants. And yeah, then there was a book by Stephen Hawking where he does a compilation of the great works by Galileo, Copernicus, and the book is called Standing on the Shoulders of Giants. So I think it's related to that. Were there any immediate technologies created further from the understanding provided by Principia, maybe engineering? Um, I mean, I think yes. I mean, I don't know exactly like how directly related, but I could say that the understanding of the laws of physics definitely led to the Industrial Revolution. So in the Industrial Revolution in the 18th century in England, we came up, of course, with the invention of the vapor machine of the vapor machine and this came because we had an understanding of thermodynamics. And as I said, thermodynamics came because we had an understanding of what is called statistical mechanics, like the how atoms work. Like when you have a mole of atoms, like Avogadro's numbers of atoms, like 6 times 10 to the 23, then people started to say, what I think is gonna be hard to apply like Newton's law to every single of these particles. So they started to think more in a statistical way. But what I'm trying to say is that you can trace all that to the revolution started by Newton. And this is one of the things that I explain to people when I talk about, for example, dark energy, or why do we care about finding the fundamental laws of physics, is when we look into history, we can find examples of how, by understanding the laws of nature, we gain an improvement in our quality of life, because that leads to an improvement in technology, and that leads to innovation. Of course, nowadays we have the known laws of physics, and we still come up with new ways of advancing human knowledge that is called innovation. But it is very hard to come up with new ideas if we don't know all the laws of physics. If we don't know about, for example, quantum mechanics, we couldn't be able to produce lasers or to have transistors, so we wouldn't have computers, for example. So the point is that once you have an understanding of the fundamental workings of the world, then you can start working your way out to technology. And another example is the understanding of electrostatic forces, right? Then that came in the 19th century, in the 18th century with Michael Faraday, Ampere, and I'm forgetting a lot, but you can see how this is working out, right? That's the more that we understand how things work out in the world, the more are the chances that we're gonna have like a practical benefit from that. And nevertheless, that's not why we do science. We do science because we want to know. No, it's a little bit a romantic point of view that I have, but it's good to point out as well that, of course, we're gonna have a practical benefit. And I always, every time I give a talk, a public talk about dark energy, then people tell me, what is that good for? And it's a very legit question, of course, but yes, this is what I tell people. I like this quote also. Tact is the art of making a point without making an enemy. Isaac Newton. I didn't know that, but maybe. Yeah. Um, there is a question. If you want to do a spectrum by Fenring H, if you want to do a spectrum analysis of an entire image, can you use some special CCD sensor, or is light of each pixel split before recording in it? So usually um, light is split before you recorded it in a CCD. So the way I have observed, maybe the experience that I have with observing has been mainly with imaging, which is just take a pictures and that's it. You don't take the spectrum, but I've also had the chance to go and take some spectra, helping some other colleagues. And usually the way it works is that you use an spectrograph and then you separate the split the light, and then you can use the CCD, the spatial dimension of the CCD, to correspond with the wavelengths of the light. So usually you split it before you record it in the CCD. The CCD is a device based on silicon that just records the amount of photons, amount of light of whatever you put at it, be it imaging or be it from a spectroscopy. Stephen Hawking is buried at Westminster Abbey along with Newton and some other great scientists. That is correct. A lot of great scientists, a lot of nobility in the United Kingdom. But I was there once, and some of the other scientists, I think they have Darwin as well. They have Maxwell, James Clerk Maxwell. He was Scottish, and he was. I said in physics, I think Newton goes first. Maybe comes Einstein, and I would say that Maxwell's come third. That's my opinion. James Clerk Maxwell. Um, So, how many kinds, astro underscore YYZ, how many kinds of black holes are there? Was reading about a black hole in a globular cluster recently. Different to supermassive black holes in large scale galaxies, just smaller. Yeah, there are different types of black holes. There are black holes. A few weeks ago, we were talking about and some news that we're talking about the discovery of what is called the intermediate mass black holes. So I was saying back in the time that we could have like basically three regimes of black holes, those that have up to 100 solar masses, and they come from stars imploding. Those are like the low mass black holes, so to speak. Then you have like the supermassive black holes that have like 10 to the 6, like millions or hundreds of millions of solar masses, that are the supermassive black holes that you find at the center of some spiral galaxies. And then there are people were seeing this gap in the population of black holes. And then the news that I was talking about a few weeks ago was referring to a discovery of one of a possible candidate of an intermediate mass black hole. And these are a little bit more difficult to find, but people have reasons to believe that they're there. And actually, this is what the news was about, that we're actually finding them. That these type of black holes that come in between the up to 100 solar masses to the hundreds of millions of solar masses. I once knew a mathematician who was working on something that did not have any applications. He was actually proud of that. Yes, I can see that. And yeah, that's great. I mean, from the mathematical point of view, that's good. I think you don't need to be working on something and that has to lead to some application. And it makes me think of, I think Lagrange. It was Lagrange. As I mentioned during this story, so first came Newton, and then the next century, a lot of people in France and in other parts of Europe started to further down his work. And I think one of the other formulations of Newtonian mechanics is what you call the Lagrangian mechanics. And I think Lagrange said that he wrote a book of celestial mechanics, and he was proud that he didn't resort to any picture or any diagram, that everything was analytical, that is to say, it was just equations. So yeah. But on the other hand, what I think is we want to pursue knowledge because all of the sake of it, and that's it. That's enough motivation for me to further the knowledge of humankind. But I think also it's great that along the way, of course, we have improvements on our way of life, and that leads to technology. And when you wanna get funding from agencies, it's good to tell them that, or to remind people that that's why it's one of the important things of why we do fundamental research. Um, how many wavelengths of light are usually imaged at a time? Is it always less than 3? That was a question by Hannes Werp. How many wavelengths of light are usually imaged at a time? Is it always less than 3? Well, usually what you do is you do it actually one at a time. Actually, it depends. So, in my experience, I've observed in a telescope in Chile called the Blanco telescope with an imager called the dark energy camera. And in that case, this is a 500 megapixel digital camera. It's a CCD camera, and you image. What you do is you have like a filter wheel, and you take images of a certain part of the sky in a certain filter, one at a time, and then you change, and then you integrate, or that means you take your data for another 100 seconds or so, or whatever you need, and so on and so forth. And then you have like 5 colors, for example, 5 filters. So then you do it one at a time. You can also maybe use the strategy of the Sloan Digital Sky Survey, where you actually had the filters lying next to each other, and then one picture of the sky, you were taking an image that had 5 colors, but in different parts of your detector. So in the end, you still do it one at a time, because you have one part of the detector, let's say in blue, and then the next part of the detector was in green. But then you wanted the first part of the detector to be in at least another 2 other bands. So then you have to move it around and then do it in that other band. So at least in imaging, that's the way you do it. You have a filter that has a certain transmission, like below and above a certain wavelength is just gonna block all the photons, all the light, and then it's just gonna pass what you call blue, what you call green, and what you call red. But of course, there are more labels than that, but it's just a range of wavelengths. And then in the end, you kind of combine these wavelengths. All the pretty pictures that you see by the Hubble Space Telescope or any other press release, that's a post-processed picture. It's just because you had to put them all together. And actually, the first person that did this was James Clerk Maxwell. Started working about taking color pictures in color. So that was pretty cool. Everybody loves black holes. That's true. I talk to kids about astronomy a lot, and they all love black holes. Yes, that's true. Pretty cool. Some psychologists must do a dissection of the love and popularity of black holes. Huh, that's a good point. Mysterious objects we're all fascinated by. Okay, thank you everyone. I think we don't have any more questions and comments, but yeah, it was a slow day, but at the same time, I think we have a nice conversation about Newton and about spectroscopy and imaging. So yes, thank you everyone. Thank you so much for watching. This has been the Daily Space. It's a production of CosmoQuest, created by the Astronomical Society of the Pacific. So please give us a like or a follow, even better, or subscribe. And yes, tomorrow, every day we'll have the Daily Space. We'll be back tomorrow at 1 p.m. Eastern, 10 a.m. Pacific time, and 6 p.m. London. Probably it will be me again. We'll see. So, yeah, hopefully you guys like me. And I'll see you tomorrow. Bye bye.